Okay. In the last class we just started off with transient analysis after doing some problems on initial conditions, and we did transient analysis on RL circuit in the last class. So, in this class we will just take it forward from RL RC with two different combinations of RL and RC circuit, and then we will wind up today's class with the RLC circuit. We will see how to find an expression for the current with respect to time. So, as I told you, the arbitrary constants involved in the solution of a differential equation can be evaluated using your initial conditions, what we saw in the previous few classes. This is what we saw in the last class, DC transient. We went through an RL circuit in the last class. We found an expression for current that was equal to V by R into 1 minus e to the minus R by L into T. I will just do this, but we did not find out what is the voltage across your R and voltage across the L as the current varies. I will just see, last class we just started off with simple RL, simple R and L. As the switch is closed at t equal to 0 with the supply voltage V, inductor value R and L, write a general integral differential equation V is equal to R into I plus L di by dt. It is just a recap of what we did in the last class. I just like to tell you how we arrived at an expression I of t, because I will be using this again and again in this class. Get an expression for, get it in the standard form, di by dt, divide this throughout by L, di by dt plus R by L into I equal to V by L. Let d by dt equal to d, therefore d plus R by L into I equal to V by L. Therefore, the root of this equation d is equal to minus R by L. So, in the last class we saw we have complementary function ICF plus IPI as two components of your current. So, ICF is nothing but A e to the power of minus the root R by L into T. IPI is your steady state current plus the current at infinity. Once the switch is closed, R behaves as R, inductor acts as a short, this is your steady state, inductor behaves as a short circuit. So, it is V by R. So, current is V by R, is nothing but I of t. To evaluate the arbitrary constants, we require the knowledge of the initial condition. So, I need to evaluate the arbitrary constant A, where my initial condition is going to help me. This is where your initial condition play a vital role. To evaluate A, put t equal to 0. At t equal to 0, I at 0 plus is A e to the power of 0 plus V by R. But what is the value at I at 0 plus? I at 0 plus, history of the network, switch is open, R, L, V, I at 0 minus is 0, network at t equal to 0 plus is a switch is closed, R behaves as R, inductor acts as open. So, current I at 0 plus is also 0. So, with the knowledge of this, substitute that here 0 equal to A plus V by R. So, A is equal to minus V by R. Substitute this in this expression, we will get an expression for the current I of t. So, current I of t is nothing but V by R into 1 minus e to the power of minus R by L into t. We saw this in the last class, we stopped here. We just got an expression for I, where V by R is a constant, arbitrary constant. Evaluating arbitrary constant, we require the knowledge of initial conditions. Now, this is an expression for current. I told you, if I have this equation A, I can plot the current waveform for different values of time. So, I can see how the current is going to increase and settle down at a value at V by R. This is your expression of y axis is I, current. For different times, I can calculate, substitute the value of t, get a value of I, plot it, you will get this. So, this has two parts, one is your transient part, the other one is the steady state part, where the current does not vary. Now, the question is, what about the voltage across your resistor? voltage across your inductor as the current varies. As the current varies, we need to calculate the voltage across the inductor and the capacitor. Procedure is almost same for any type of circuit. So, we will see this, what happens to the voltage across the resistor and the inductor as after the switch is closed. Voltage across the resistor is I into R, voltage across the inductor is L di by dt. This we know, we have used this many times. So, voltage across the resistor will be, voltage across the resistor is, just multiply this equation by R and R cancels, means it is I is R into V by R into 1 minus e to the power of minus R by L into T, R will cancel. So, I will be left with voltage across the resistor is V into 1 minus e to the power of minus R by L into T. This will be the voltage across the resistor. Similarly, the voltage across the inductor is L into the derivative of di by dt. I have an expression for I. So, voltage across the inductor is equal to L into the derivative of I of t, I of t. So, V by R into 1, derivative of that is 0. So, this derivative becomes 0 minus V by R, minus of V by R e to the power of minus R by L into T into minus R by L. This is the derivative of the current. So, this R will cancel with this, L gets cancelled, minus into minus becomes plus. Therefore, the voltage across the inductor will be plus V e to the power of minus R by L into T, e to the power of minus R by L into T. So, this is an expression for VR and VL. If you just try to plot these two voltages as time varies, let us see how it looks. We get a very important information from this. Voltage across the resistor when t equal to 0, 1 minus 1 is 0. So, it starts at 0. Then as t goes to infinity, this goes to 0. So, it is V. Voltage across the resistor keeps on varying and reaches a value, whereas this value is equal to V. This is what indicated by this equation. This equation tells us that voltage across the resistor is this, means this is your VR varying with time. If you just see VL, when t equal to 0, if I plot the other curve, t equal to 0 means 1, it starts at V, means voltage across an inductor will have a value V, and then gradually it dies down to 0. So, this is your VL with time. What is that we can understand? The current is varying this way, this is a expression I of t, this is what given here. The current varies exponentially, the voltage across your resistor, the voltage across your capacitor is as shown. This is the voltage across your resistor VR, this will be the voltage across your inductor VL. Voltage VR across this and VL across this. What information this gives? The sum of voltages at any point of time, means at any instant of time here, VR plus VL is equal to the supply voltage, means KVL is proved. The total voltage applied is equal to the voltage across your R and voltage across your L. When the voltage across the resistor is 0, the inductor voltage across the voltage of the inductor is V, and when the voltage across the inductor goes to 0, voltage across the resistor is V. Indicates this, you can just look at the initial conditions, the way they behave. At t equal to 0 plus, immediately after switch is closed, your inductor behaves as a open circuit. Inductor acts as open circuit means all the voltage V appears across this. There will be no current, current is 0, current becomes 0, but the voltage across the inductor is nothing but V, that is what indicated by this. But because the current is not there, R is there, the voltage across this is 0, that is what is said this. If you just say at t equal to infinity, it will be switch is closed, R, inductor acts as a short, voltage across the inductor is 0, voltage across the resistor is nothing but your supply voltage V, that is what we can see here. So, we get a lot of information from the values what we obtained VR and VL. So, that is what is indicated here from this circuit. So, this is a transient analysis for a RL circuit. We will go to the other circuit RL. We will take up RL circuit, but slightly different, where the switch is earlier closed at 1 and when the switch is moved to position 2. We called this as A and B in the previous case. The only difference between this circuit what we are looking at is this. The same RL circuit, position 1, position 2, the switch is connected to 1 and moved to 2 at t equal to 0. Let us see how to obtain an expression for current in this case. What will be the current when the switch is moved to position 2? Already when the switch is at position 1, steady state has been established. There will be a current flow through the inductor because inductor will act as a short in steady state. Then the current is moved to position 2. Gradually the current dies down, there is no forcing function. Gradually the current dies down in this loop to 0. So, we will find an expression for current and we will see how to find the voltage across your resistor and inductor in the same fashion. So, in different problem RL circuit, we will see what will be the expression for current in this case. As usual, write the integral differential equation after switching for a general network. That means we will have some initial knowledge, initial conditions at t equal to 0 minus, switch is at position 1, switch position 1, steady state has been established, steady state has been reached, means this will be the circuit. Switch is at 1, R, your inductor will act as a short. So, what is the current through this? I at 0 minus will be V by R, V by R. If the switch is moved to 2 at t equal to 0, network at t equal to 0 plus, network at t equal to 0 plus, switch position 2, moved, R behaves as R, this acts as a current source of value, this is position 2, V by R is your initial current I naught, this acts as a current source, therefore, I at 0 plus equal to V by R in this. We have seen this even in initial conditions. We will see how to obtain this knowledge will help us in evaluating the arbitrary constant. After the switch is moved to 2, write the general expression. This is R, this is L, this is position 2. So, we get 0 equal to R into I plus L di by dt. Get this to the standard form, di by dt plus R by L into I equal to 0 means d plus R by L into I equal to 0, d equal to minus R by L, same root because it is RL circuit. So, I of t will have I complementary function plus the particular integral. Here there is a small change, complementary function of current will be an arbitrary constant A into e to the power of minus R by L into t. because the root I get an expression for the complementary function because the transient part of the current which dies down with time, okay, plus particle integral. What is the steady state value of the current? Steady state value in this loop will be 0. Final state, finally what will be the current here? This is initially acting as a current source, but finally this acts as a short, but there will be no current because there is no forcing point, there is no voltage applied. So, at t equal to infinity, the circuit will be R and L, current I at infinity will be 0, that is what the current Pi, particle integral, is the steady state current. This is your transient current. So, these two put together is the expression for current I of t, how it varies with time. We will just see how to evaluate the arbitrary constant A. Substitute for I at t equal to 0 plus as A e to the power of 0. What is the current at 0 plus? We just now saw the current at 0 plus is V by R. Current at 0 plus is V by R. So, I at 0 plus is V by R is equal to A. Therefore, I got the arbitrary constant. This is what we keep telling. To evaluate the arbitrary constants of a differential equation, initial conditions are essential. So, substitute this in your equation, we get expression for current I of t as V by R e to the power of minus R by L into t. How does the current vary here? Current exponentially decays to 0 with time. If I just plot the current with time, current on your y axis, you can just see that the current dies down because once the switch is close to 2, the current in this loop, because it acts as a current source, gradually it starts at V by R, current at 0 plus, immediately after the switch is closed, at t equal to infinity the current will be somewhere here, it starts at V by R, t equal to 0 this becomes 1 V by R, at t equal to infinity this becomes 0, this term becomes 0, therefore the current dies down to 0. So, the current gradually exponentially decays to 0. This will be current I of t is what we obtained for a RL circuit of type 2. When the switch is moved from 1 to 2, the current in this loop gradually reduces to 0. Similarly, we will find what is the voltage across your resistor, what is the voltage across the capacitor. Voltage across the resistor, across the inductor or the capacitor, we will check up RC next. Voltage across the resistor is R into I of t, which is R into I of t is V by R into e to the power of minus R by L into t. R and R will cancel. So, I will be left with V by R as voltage across the resistor is V e to the power of minus R by L into t as 1. Similarly, voltage across the inductor is L di by dt, which is L derivative of this. It is V by R e to the power of minus R by L into t into minus R by L. R, L and L will cancel. This minus sign will come out. So, voltage across your inductor will be minus. Be very careful with these symbols, this sign. If you take it plus, it becomes wrong. It is minus of V e to the power of minus R by L into t. It is V e to the power of minus R by L into t. We just plot this voltage across the resistor and inductor, we will have some idea about how the voltage across these two varies with time. We just plot voltage across the inductor and capacitor. It is V, voltage across the resistor at t equal to 0 is V. When you put t equal to 0, t equal to infinity, this goes to 0, this term goes to 0, I will be left with a 0. So, exponentially the voltage across your resistor decreases, we are varying with time. What happens to the voltage across your inductor? Voltage across the inductor will be minus V e to the power of minus r by L into t at t equal to 0. This will be your voltage across your inductor at with varying time. It starts at V, this will be minus V. What does this indicate? And it goes on, because the current dies down to 0. We have seen that the current V by R e to the minus t by R c, this will be dying down to 0. It starts the current expression 0. The voltage across the resistor will also follow the current. This will be this way. Means at any point of time, if you just take the total voltage in the loop is equal to 0, and it proves your Kirchhoff's voltage law. KVL is proved, right? VR plus VL is 0, right? In this loop, the voltage across the resistor plus the voltage across the inductor will be 0, and it is opposite. You can just see those two are parallel, right? So, the voltage decreases, the voltage increases, effectively the current will be, the voltage across these two will satisfy your Kirchhoff's voltage law, KVL, VR plus VL equal to 0. So, this is the two combinations of RL circuit. I think with this you can understand how the current varies, how the voltage across the resistor, inductor varies and so on. This is the voltage across your resistor, how it varies with time. This is voltage across your inductor with time. I told you at any instant of time VR plus VL will be equal to 0. In the previous case, it was VR plus VL was equal to the supply voltage. Just see the difference between the previous and this. But as here it is VR by VL, VL is minus. So, it is minus of V to the minus R by L into T. The time constant, normally what we say, tau is L by R. In the expression it is e to the power of minus T by tau. Tau is L by R. So, it is e to the minus R by L into T. This is your time constant of the circuit. So, we have just taken RL, we have just taken RL circuit where the switch is closed from 1 to 2, right, without any forcing function. We will go to the RC circuit now. This is a RC circuit DC transient. Same way we need to start, write the integral differential equation, obtain the expression for I, means ICF plus IPI, and we will get a equation I of t is V by R e to the minus t by RC. So, probably at the end you will be having everything by heart, the expression for current in case of RL circuit, behavior of the elements and so on. So, we will take RC circuit, how the current varies, and we will plot again there we are voltage across the resistor and voltage across the capacitor. So, the knowledge of initial conditions will help us everywhere. So, a simple RC circuit, switch is closed, R and C, this is supply voltage V, DC, R and C, switch is closed at t equal to 0. History, initial conditions at t equal to 0 minus, I at 0 minus is 0, voltage across the capacitor at 0 minus is 0. At t equal to 0 plus, if you write the network, R behaves as R, capacitor acts as a short. So, I at 0 plus is V by R in this case, because I have a current flowing through, because it acts as a short circuit at t equal to 0 plus, because it is an RC. Therefore, your current at 0 plus is V by R. We will see where this is going to help us. As usual, we write the integral differential equation V is equal to, for a general network after switching, V is equal to R into I plus 1 by C integral I dt. What we found in the previous case was a solution of differential equation. I got an integration here, differentiate this to bring it to the standard form, differentiating A, we get 0 because this is DC. If this is not DC, then the derivative of sine or cos any function has to be taken care while doing a differentiation. 0 equal to r di by dt plus I by C. Get this to the standard form, divide by r, because the coefficient should be 1, di by dt plus I by RC equal to 0. So, if I find the root d plus 1 by RC into I, d equal to minus 1 by RC. So, the complementary function IC, I of t will have complementary function plus the particular integral. The complementary function will have an arbitrary constant a e to the power of minus t by RC, a e to the minus t by RC. What about the particular integral? Plus particular integral is steady state current. Steady state current is the behavior of the element at t equal to infinity. T equal to infinity, the capacitor acts as open. Capacitor will act as open. So, current will be 0. At t equal to infinity, is called as steady state. After the switching, right, the behavior of the circuit will be switch is closed, R behaves as R, capacitor acts as open. So, the current in the circuit at infinity will be 0. So, this is your steady state current. This part is your steady state current IP. So, this is an expression for I of t. So, how do I evaluate A? Substitute for t equal to 0, at t equal to 0 plus, I at 0 plus is A e to the power of 0. I at 0 plus, we know that we have an expression V by R, I at 0 plus. This is the expression for current at 0 plus, which is very important. I at 0 plus is V by R equal to A. Substituting this here, I get I of t equal to V by R e to the power of minus t by RC. This is an expression for current. We can easily understand from by looking at the circuit. Once the switch is closed, right, current starts at V by R as given here, and then it dies down to 0 gradually. That is what your equation infers. If I just plot expression for I of t, I with respect to time, it starts at V by R when t equal to 0 and gradually dies down to 0. This is I of t. Now, similarly calculate the voltage across your resistor and voltage across the capacitor. This is what current V by R e to the minus t by RC. Now, we will see how to calculate VR and VC. How do you calculate VR and VC? VR is I into R, VR is I into R, just remove R and R, you get an expression for voltage across the capacitor. Voltage across the capacitor is given by V e to the minus t by RC. VR is R into I, V by R e to the power of minus t by RC. So, it is V e to the power of minus t by RC is VR. What is voltage across the capacitor? Voltage across the capacitor VC is 1 by C integral I dt, but we have a constant integral constant plus the constant C. We need to really worry about this constant, otherwise we will have a wrong answer. This constant, this voltage, final voltage will be V and its forcing function is V. It is closed, the switch is closed, the final voltage will be V and there will be a forcing function V applied to the capacitor voltage. So, this C will be equal to V. So, if I just take VC is 1 by C integral I dt plus the constant, this is the integral constant, right, which comes along with the integration V. this is equal to 1 by c integral of I is v by r e to the minus t by r c, v by r e to the power of minus t by r c divided by minus 1 by r c. This r c will cancel. Of course, that plus v will be there, the integral constant, r c will cancel, this will be minus. Therefore, if I write voltage across the capacitor, it will be v into 1 minus e to the power of minus t by r c. So, I get VR, I got VC, voltage across the capacitor. If you plot the voltage across the resistor and voltage across the capacitor, you will get a expression, or sorry, the waveform with respect to time, and the voltages, component voltages will be one will be increasing and the other will be decreasing curve. So, this will be your voltage across the decreasing curve, will be your voltage across your resistor, this will be voltage across your capacitor. So, if you plot these two, one will decrease, the other one will increase. At any point of time, the total voltage is equal to the supply voltage, VR plus VC is equal to V. So, V supply voltage will be VR plus VC, voltage across the resistor plus voltage across the capacitor. So, this is what we found RC circuit. We will take a similar example what we took for RL. We will take a RC circuit and we will see how to find the current, expression for current in a circuit when the switch is moved from 1 to 2. Switch is initially at 1 and it has reached steady state. What happens when the switch is at 1? When the switch is at 1 and it has reached a steady state, your capacitor acts as open circuit, final state of the capacitor with a voltage VC across that. And when it is moved to 2, when the switch is moved to 2, this capacitor acts as a voltage source. What will be the direction of current? The direction of current, please see, this is with plus and this is polarity minus. With the assumed direction of current, the current will be driven in the opposite direction in this case, right. So, this capacitor, a charged capacitor, charged is because it is at position 1 before and the switch is changed to 2, this top plate having positive, it drives the current in the opposite direction. Therefore, the direction of current with the assumed direction is negative, right. So, we will see that the only change in the previous circuit is I have a voltage applied. Initially, the switch is at position 1 and it is moved to position 2 at t equal to 0, and this is your positive direction of current. So, with this we will see how to obtain an expression for I, and we will go to RLC circuit, and what we are taking here is all general networks. The only change will be with some numericals. In the next class we will take up some numerical problems along with this. So, for the second type of RC, this helps us in analyzing any type of circuit, right. So, we have taken RL, two types RC. So, after the switch is close to 2, if I want to write an expression for voltage 0 equal to R into I plus 1 by C integral I dt, a simple expression for general integral differential equation, right. Differentiating this equation 1, I get 0 equal to R di by dt plus I by C, divide throughout by R, I will get di by dt plus I by RC equal to 0, d plus 1 by RC into I equal to 0, d is equal to minus 1 by RC. But expression for current I of t equal to ICF plus IPI. Complementary function is, I got a root, it is A e to the power of minus T by RC, correct. What will be the particular integral of current? What will be the current in this case? Finally, in this final state at t equal to infinity, switch is moved to 2, capacitor acts as open, no forcing function, the current will die down to 0 in this loop. Therefore, this is 0 equal to I of t. To evaluate the arbitrary constant A, I need to know the initial knowledge. So, what will be the initial value? When the switch is moved to 2, at I 0 minus, the capacitor, I 0 minus is 0, voltage across the capacitor at 0 minus will be V. At t equal to 0 plus, if I write the network, after the switch is moved to 2, if I write the network of this circuit, it will be R capacitor with a voltage V. This is how I can write. What will be the current? I at 0 plus will be, it will drive a current in the opposite direction, because this is R, it is V by R. V by R with a negative sign. This negative comes because this is the assumed direction of current. Assumed direction of current is clockwise, this is drives the current in the anti-clockwise direction. Therefore, I at 0 plus will be A e to the power of 0, it is minus V by R is A. Therefore, an expression for current I of t is minus V by R e to the power of minus V by R e to the power of minus T by RC. This is an expression for current being obtained for a RC circuit. This is what we have seen. For RC, after the switch is moved to 2, right, the circuit will be R and C. Expression for I of t, how the I varies with time is given by this. What about VR and VC? In this loop, the voltage across the resistor and capacitor have to be 0. Therefore, if you just see what is VR, VR is I into R. So, it is minus V e to the power of minus T by RC, because VR is I into R. I have an expression for I, R cancels. So, I will left with V e to the power minus T by RC. What about VC? 1 by C integral I dt plus the constant, plus the integral constant here. What will be the integral constant in this case? In this case, the integral constant will be 0, because there is no forcing function, it is connected to a short, and final voltage across the capacitor also will be 0 in this case. Vc is equal to 1 by C, integral of I is minus V by R e to the power of minus T by RC by minus 1 by RC. RC will cancel, RC and RC will cancel out, minus and minus becomes plus, it will be V e to the power of minus T by RC is the voltage across your capacitor Vc. If you plot these two, what will be the voltage across your resistor? Voltage across the resistor is minus V e to the power of minus T by RC, just see here. Voltage across the capacitor is V e to the power of minus T by RC is what we have got. So, at t equal to 0, voltage across the resistor will be minus V, voltage across the resistor will be minus V. This is your VR, voltage across the resistor at t equal to 0 will be V. So, it starts here, this is your Vc. At any point of time, the sum of the voltage is equal to 0, right, because it is connected to a short. I think with this we have to get into, we have completed RC, go through this carefully, step by step, and try to understand how to obtain an expression for I of t. Once the expression for current is obtained, finding all the VR and VC is a very trivial problem. So, the last one what is left is RLC circuit. We have to take up RLC. The only issue in RLC, as all of you know, what we are dealing till now was a first order differential equation in RL and RC. The only difference in RLC is it becomes a second order differential equation. So, we will have two arbitrary constants and we have three different cases there. We will just see RLC circuit now. So, this is a DC transient analysis of okay. Madam Dale. So, what we are seeing now is a DC transient RLC circuit. So, RLC is a series RLC, the circuit is simple, series R, L and C connected to a DC supply. So, once we have a simple RLC connected to a DC, start off with writing the integral differential equation RLC R, L and C, which is closed, V equal to R into I plus L di by dt plus 1 by C integral I dt. To get this to the standard form, I will differentiate this equation. So, differentiate this equation will be R di by dt plus L d squared I by dt squared plus I by C, call this equation B, divide the out by L to get it in the standard form. I want the second derivative, coefficient of the second derivative to be 1, therefore, d squared I by dt squared plus R by L di by dt plus I by LC equal to 0. To find the roots, it is d squared plus R by L into d plus 1 by LC into I equal to 0. If I say d by dt is d, if d by dt is equal to d, so this second order equation will have two roots. How do we find the roots? It will have two roots, R1 and R2. The two roots will be minus b, root of a second order equation, simple, minus b plus or minus root of b squared minus 4ac. So, roots will be minus R by L minus b plus or minus root of b squared minus b plus or minus root of b squared minus 4 ac. It is 4 ac is 1 by LC divided by 2 into a, 2 into 1, don't take it as 21, it is 2. If I just absorb this 2 here, it will be minus R by 2L, roots R1 and R2 will be minus R by 2L plus or minus, if 2 comes here, if it has to go inside, it becomes 4. So, 4 inside this bracket becomes 2, it is R by 2L whole squared, of course, it is a root, minus 4 cancels 1 by LC. This is the actual roots of a second order equation. roots of second order equation is minus r by 2l plus or minus root of r by 2l whole squared minus 1 by LC. This is important. Now, this leads to three different cases. First one is r by 2l whole squared. We will just see what are the three different cases here. My roots, two roots are there for the second order equation in RLC circuit. This term r by 2l whole squared can be equal to 1 by LC, can be greater than 1 by LC, can be less than 1 by LC. So, on this it will be an overdamped, underdamped, critical damped circuits. So, if r by 2l whole squared is greater than 1 by LC, I will get two real and distinct roots. If r by 2l whole squared is equal to 1 by LC, the whole term goes to 0, I will have two repeated roots at minus r by 2l. If r by 2l whole squared is less than 1 by LC, I will get a complex conjugate root. It is this term plus j and minus j something, because this term is less than 1 by LC. So, I will be arriving at three different cases in a RLC circuit. We will extend this in the next class. So, case 1, case 2, case 3, overdamped, underdamped, critically damped circuits depending on the term inside the root. So, r by 2l whole squared can be greater, less or equal to 1 by LC. So, this decides what type of circuit, how it behaves. But one thing you need to know, in a RLC series circuit, the initial current will be 0 because of the inductor after the switching, and final current through this loop also will be 0 because of the capacitor. The initial starting current will be 0 because the inductor is there, it does not allow any sudden change, and finally the capacitor acts as open, inductor acts as short, the current will be 0 even in this case. Therefore, it is 0 in both. We will see, we will extend this and we will take up some numerical problems tomorrow on RL, RC and RLC, and we will wind up this particular unit tomorrow being the last class for this particular chapter. Any doubts, you can just contact. This is what I said, RLC can be overdamped, critically damped and underdamped. We will see this tomorrow again. Thank you.